Good morning. Good morning to everyone. Right. Still the students has to come. One minute. Okay. So what I will do is, I will explain whatever has been taught in the last class. Fine. So now, when it comes to last class, can any one word, can you tell me? Can any one of you? Can one word, what we have taught what we have studied in the last class? One of the important concept we have discussed. Which is that? Okay, Jannavi. Lanthanoid facts and consequences. Okay, so what do you mean by lanthanoid facts? Yes, that's where we have discussed about lanthanide contraction, right? And I told this is very important, right? So what we have discussed in the last class was related to lanthanide contraction. What is the reason, right? First thing is what you mean by lanthanide contraction. Then why it is happening? So we have to answer this question, right? So lanthanide contraction means it is decrease in the atomic size more than the expected one. That's where we have the lanthanide contraction. So what is the reason? Yes, Suresha. Okay. Then we have discussed about oxidation states. Yes, I will come to that. So that's where we have the lanthanide contraction, which is nothing but decrease in the atomic size more than the expected. Right? So why there is a decrease in the atomic size? Due to the involvement of F subshell. Right? So when I am talking about 5D series, lanthanide contraction is related to 5D series. Now when I am talking about 5D series, there will be filling of 4F orbital. There will be filling of 4F orbital. So due to that, what will happen? Due to the less shielding effect shown by the F orbital, so due to that there will be contraction of the atom will take place. So it will lead to decrease in the atomic size. So that is the definition and reason why it is happening. We can combine these two to define the lanthanide contraction. That is also fine. So you can tell that since there will be involvement of 4F orbitals with respect to 5D series, due to that there will be decrease in the atomic size more than the expected values. So that's where it is called as lanthanide contraction. Anything is fine. So what is the consequence? Consequence here is when it comes to lanthanide contraction, due to that 5D elements, whichever belongs to 5D, they will be having higher density. They will be having higher density. That is one of the reasons. They will be having higher density. Right? Then, what else? What is the another consequence? Another consequence here is 4D and 5D element. Corresponding elements. They will be having almost similar atomic size. They will be having almost similar atomic size. That's what we have discussed in the last class. Then, you people have written, we have discussed about oxidation states. Yes, definitely we have discussed about the oxidation states. right? So when it comes to oxidation states, I had taken the example of 3D series, right? So where scandium to manganese, we have one type of character, and iron to zinc we have the another type. Where in scandium to manganese, if you recollect, minimum oxidation state will be the number of electron present in the S subshell, right? Number of electron present in the S subshell. Then maximum oxidation state will be total number of electrons present in S subshell and D subshell. That is applicable here. Where manganese will show highest oxidation number, that is +7. When it comes to iron to zinc, here we have minimum oxidation which will be equal to number of electrons present in the S subshell. But higher oxidation state will be S subshell electron plus lone electrons or unpaired electrons present in the D subshell. That is the difference between these two. Right? All of you will agree? And zinc is the one which will show +2 oxidation state. It will prefers to show only one oxidation state, that is +2. So that's what we have discussed in the last class. Then you people have written with higher melting point and all. Yes, that we have discussed not in the last class, before that one, that is related to physical properties. Right, that is related to physical properties. Yes, manganese is the one which will have the highest oxidation state, that is +7. Okay. Now we will come to next one which we had initiated in the last class, and we are going to continue the same thing. That is redox potential related to M+2 M. Okay. So now this is called as redox couple. If you recollect, in a redox reaction people have discussed. So this is called as redox couple, where general naming we have given, where M can be any of the 3D series element. Any of the 3D series element. And same thing will be applicable for 4D, 5D, 6D. No need to worry. Normally they are going to concentrate on 3D series. So that's where we have the general representation of the redox couple. So what it tells, M+2 M, that means if I take zinc, then it will become zinc +2 zinc. If I take manganese, then it will become Mn+2 Mn. So that's where we have the nomenclature, or that's what it represents. M+2 / M stands for, it is a redox couple. Now, as I have told in the last class, we have hydrogen. We have the hydrogen. If I am going with elemental form, then I can take it as like this. Now, this particular couple, redox couple, will have the 0 electrode potential. The redox potential for this one is 0. So that's what we have assumed, or 0 volt or 0 millivolt, whatever it is. So that's where it will be having 0. That's what we have represented, which you have studied in your electrochemistry. Standard hydrogen electrode, She. Right? So that's where we have the condition. Now, if you know the electronic configuration, say for example, if I take zinc, it will be 3D10 4s2. If I take manganese, then argon 3D5 4s2. So this is the condition, right? So if I take scandium, so in that case, if I am talking about scandium, it will be having argon 3D1 4s2. So that's where we have the condition, electronic configuration. Now if you observe it carefully, zinc and manganese, I am talking about the reaction where zinc is going to get converted into zinc plus 2 electron. Manganese is getting converted into Mn plus 2 electron. So this is the reaction. Now if I consider this one as a reversible reaction, to make you understand I am writing this. If I consider this one as a reversible reaction, in that case I can write it as like this, right? So this is the scenario. Now can you tell me if this is forward reaction, this is backward, forward, backward. Now for these two reactions, which one is preferred? Forward or backward reaction? Which is going to be preferred? Forward or backward reaction? Which will happen? Easily. That's what my question here is. For that particular reaction where zinc is getting converted into zinc ion and 2 electron, manganese is getting converted into Mn plus 2 electron. Can you tell me which one is going to be preferred? Either this direction or either this direction. Now someone has written, Purnima, she has written forward reaction, right? She has written it as forward reaction will be preferred. Okay. Even Ravikant is telling, yes, forward reaction. What should be the reason then?
Completely different.
The reason here is whenever they are going to donate the 2 electron, that means if I am talking about zinc plus 2, then it will become argon 3d10. If I am talking about Mn plus 2, then it will become 3d5. So that's where they are attaining the stability. So what I mean to tell here is, whenever zinc is getting converted into, which we have already discussed when I was talking about electronic configuration. So when I am talking about zinc, so where we have argon 3d10 4s2, and when we are talking about manganese, where we have argon 3d5 4s2. So this is what is happening when they are losing the 2 electrons, right? So that's what it is happening. But when it comes to scandium, I am taking the example of scandium, argon 3d1 4s2, and it's becoming scandium plus 2, argon 3d1, right? So that's what it will happen when it comes to scandium, if it is losing the 2 electrons. So if you observe it carefully, these two elements are the one which are attaining the stability once they are losing the electron. They are attaining the stability once they are losing the electron. But for other element, that will not be much matter, right? That's not going to much matter when I am talking about M plus 2M, standard redox potential. So due to that, since these are the two elements which can easily donate the 2 electron, so they will be having negative standard redox potential value. They will be having the negative standard redox potential value. Fine. So negative in the sense, if for example, so they might be having somewhere around minus 0.82 minus 1.1, something like that. Approximate values I am writing. Minus 0.82 minus 1.1 millivolt or volt, whatever it is. Okay, na? So they might be having that particular value. But if I take scandium, even it will be having negative value, no doubt. Even scandium will have the negative value, but that negative value will be somewhere around 0.3, 0.3. Now I am talking about approximate value. Okay, so most of them they have the negative value. Even it can go up to other elements like titanium and all. If it will be somewhere around 1. For titanium and all, it will be somewhere around 1 minus value. Okay, so what is this minus value indicates? Minus value indicates that they will be losing the 2 electron easily. That's what you should remember. They are going to lose the electron very easily. Fine. So that's what it indicates. So they are good donors of electron to even hydrogen. H plus. What I mean to tell here is for H plus. They are going to donate the electron to H plus because for them it is higher than the negative, that is 0. So therefore scandium, which is around minus value only, titanium minus value only, zinc, manganese minus value only. They are all very good donors of electrons. To whom? To the H plus. So that's what these values indicates. Fine? All of you have understood? But we have one of the 3D series element. We have one of the 3D series element which will not have the negative value. One of the 3D series element which will not have the negative value is copper plus 2 copper. This particular redox couple does not have the negative value. They have the positive value somewhere around plus 0.3. No need to remember the values and all, but you should remember which will be having negative and which will be having positive. So this is one of the element which is having the positive redox potential value. So positive plus, that means it is greater than 0. It is greater than 0. That means copper cannot donate the electron. So what I mean to tell you is this particular reaction will not take place easily. This particular reaction will not take place easily. That's what this positive value indicates. So what I mean to tell you is, compared to hydrogen as a redox couple, if I compare that one with the copper as a redox couple, hydrogen redox couple is going to dominate when it comes to donation of electron compared to the copper. Fine? So that's what these values will indicate. Now, due to that, yesterday we have discussed that, due to that, copper will not react with HCl or some of the acid. HCl is not going to react. The speciality of this HCl here is it's a strong acid. It's a strong acid, but as a molecule, it's not a strong oxidizing agent. That is the reason. That's why copper is not going to react with the HCl. But the same copper, when it reacts with HNO3, concentrated HNO3, when it reacts with concentrated HNO3, it's going to form cupric nitrate. It's going to form cupric nitrate plus NO2 plus water. NO2 plus water. So that's where we have the reaction. So we have to balance it, right? So if I make it as 3, whether it is balanced? Okay, nitrogen will not get balanced. So we cannot go with the 3. So I will make it as 4. So 2NO2, 2H2. I think it should be balanced. It's balanced. So that's where we have the reaction. Now, same copper is going to react with concentrated HNO3. It's not going to react with HCl. Okay, now, same copper, it can also react with the sulfuric acid, concentrated sulfuric acid. With dilute sulfuric acid, even with the dilute sulfuric acid, the reaction will be very slow. Okay? So therefore, concentrated sulfuric acid, it's going to form cupric sulfate. It's going to form cupric sulfate, SO2 and water. SO2 and water. Fine? So that's where we have the reaction. 1 minute, we have to balance it. We will see with the 2. I think it is balanced now. So that's where we have the reaction. Copper, which is not going to react with HCl, now the same copper is going to react with the nitric acid, that is concentrated nitric acid and concentrated sulfuric acid. Even people will tell we can use hot concentrated sulfuric acid, that means bit high temperature we have to maintain for these reactions to happen. So what I mean to tell here is, what is the reason why copper is not going to react with HCl and all? That is because of the positive redox potential value. That is due to the positive redox potential value. But why they are going to react with nitric acid and sulfuric acid and all? That is because of the oxidizing character. Sulfuric acid and nitric acid, not only they are strong acids, along with that they are very good oxidizing agents. So therefore they are able to react with the copper. Any doubt? So this is what we have to remember. We will move to the next one. Okay. So next one is M plus 3M as the example. Redox couple. M plus 3M. So now what do you mean by M plus 3M? If I am going with manganese, then it will become Mn plus 3 manganese. If I am going with the zinc, it will become zinc plus 3 zinc. If I am going with scandium, it will become scandium plus 3 scandium. So these are the examples. Common examples only I am taking. Okay? Right? So in that case, which one you feel it will have the positive value, or if I am taking it as iron? Okay. So which one do you feel? Okay.
Scandium and iron.
Fast. You should tell me.
Iron will have.
Which one? Iron will have negative or positive?
Negative.
Okay, according to Mayank, iron will have negative value. What else? Okay. Now when I am talking about this particular redox potential, one thing we have to consider here is hydration enthalpy. Okay. So hydration enthalpy means how easily iron is going to get solvated. A formed iron is going to get solvated. That is hydration enthalpy. So before that we have the sublimation enthalpy. Okay. So where ions, metals will get converted into gaseous state, then they are going to lose the electron. Sublimation enthalpy, then hydration enthalpy, then ionization enthalpy. So these are the 3 points which we have to consider. Okay, and one of the concept which is going to affect these factors here is electronic configuration, no doubt. But along with that, these are the some of the factors which we are going to consider. Now, when I am talking about Mn plus 3, it's not so easy, because when you are removing the another electron, you are disturbing the stable electronic configuration which manganese has attained. Or to be more specific, I will make it as plus 2, plus 2, plus 2. So I will make it like this. Means next step. Already we had manganese ion, and from that another one electron we are removing. So if that is the case, it has attained the stability, you are disturbing this one. So it will have the positive value. So what about zinc? Definitely, since it has attained the stability in the zinc plus 2 form, so since you are removing the electron from that stable one, so therefore it is going to have the positive value. What about scandium? What about scandium?
Negative.
Huh? What is the electronic configuration of scandium plus 2? It was argon 3d1. It was argon 3d1. So Ravikant, yes, it should have high negative value. That is because once it will lose the another electron, that means scandium plus 3 will be having electronic configuration of argon. It will have the electronic configuration of argon, that is 3s2 3p6 it will become. So scandium will have the high negative value when it comes to plus 3 from plus 2. Okay, plus 3 from plus 2. Now, what about Fe plus 3? Fe, it is 26. It is next to the manganese. So that means it should have 3d6, that means argon 3d6 4s2. 3d6 4s2. What should happen? First, Ravikant, positive. Okay, according to Ravikant, it should have the positive value. Okay. Why positive value? Say for example, if I am talking about Fe plus 2, it will become argon 3d6 4s0. If I am talking about Fe plus 3, argon 3d5. So that means it is attaining stability, right? Fe plus 3. Then why it should have the positive value? Manganese and zinc we understood. It is having positive value, no doubt. What about this one? Whatever Ravikant has told is correct. It will have the positive value. Therefore, in the beginning only I told, not only electronic configuration, it is the other factors which are also going to decide what should be the redox potential value. It is not only related to electronic configuration. So please remember, although Fe plus 3 will have the stable electronic configuration, okay, compared to Fe plus 2, but still they will be having positive redox potential value. They will be having positive redox potential value. All of you have understood? Fine. But scandium straight away we can tell, because it will attain the electronic configuration of argon. So due to that it will have the negative redox potential value when it comes to triple positive charge. Okay. So that's where we have the concept. So we will move to the next one. Any doubts? Any doubt? Then we have, okay, then we will move to the very important one, that is magnetic properties. Very important one. That is magnetic properties. Okay, na? Now, when I am talking about magnetic property, so with related to paramagnetic, diamagnetic or ferromagnetic, so that's what we are going to focus when it comes to magnetic property. And all of us will know when it comes to 3D series, we have iron, nickel and cobalt. So these are the some of the examples where they will be example for whatever I have written on the board. They are the examples for wow. Whether it is there? Okay, it should be there. It should be there. Anyway, we have discussed this one in solid state topic.
Magnetic substance.
No. I want one particular word.
Ferro or paramagnetic.
So they are ferromagnetic in nature. They are ferromagnetic in nature. They will show ferromagnetism. So what do you mean by ferromagnetism? Ferromagnetism means where they will be having strong magnetic property. They will be having strong magnetic property, or they can be converted into a magnet if you provide the condition. So that's what iron, nickel, cobalt, they are the one. Now if that is the case, we have some of the element which will be paramagnetic, which comes under 3D series only, which are nothing but paramagnetic. But at the same time, in the 3D series we have element which are diamagnetic. We will see. So which are those? Ferromagnetic substance we have already discussed. That is iron, nickel, cobalt. They will be the one which will be ferromagnetic in nature. But when it comes to 3D series, we have even paramagnetic also, diamagnetic also. Now when I am talking about diamagnetic, all of us will know when we have the paired electrons, or when there is an absence of unpaired electron, those are the element which can show the diamagnetic property. So which are those which don't have any unpaired electron? Leftover unpaired electron should not be there. So those elements are the one which will normally show the diamagnetic character. Can anyone tell me which is that one in a 3D series? Which should be that one?
Zinc.
It should be zinc. Mayank has told it should be zinc. Correct. Okay. Now when it comes to paramagnetic, so it should have unpaired electron. Then only they can show the paramagnetic property. Yes, Ravikant, it should be zinc. Purnima, even you are right. So when it comes to paramagnetic, they should have the unpaired electrons. Okay. Then we have plenty of example. Like manganese, scandium, titanium, vanadium, so many, chromium, all of them, they are the example for paramagnetic substance. Got my point? They are all the examples for paramagnetic substance. Now you should tell me Based on that, we should have the highest magnetic property in that case. Which one should have the highest paramagnetic character among these? Which one should have the highest paramagnetic character? So we have scandium, then titanium, vanadium, chromium, manganese, cobalt, nickel, then copper and zinc. Oh, only 9 it has become. One element. Okay. So among these, which one should be? Oh, iron only I am asking.
Iron is ferromagnet.
No, simply I am asking. If I consider all of them, ferromagnetic will be paramagnetic property, they should show, no doubt. So among these, which one will be having highest paramagnetic character? Okay, Ravikant is written zinc. Ravikant, titanium, Jahnavi, manganese, Purnima, scandium, okay, all different elements. So I will go with manganese. I will go with manganese if that is the case. Because what it tells, unpaired electron, and according to me, as there is an increase in the number of unpaired electron, they should have the high paramagnetic property. And manganese is the one which is having highest unpaired electron. Why? Because it is having, manganese is having 5 electron in the d subshell, and the 5 electron should be unpaired electrons. All the 5 electrons should be unpaired electrons. No other element will have the so many unpaired electrons in their d subshell. Right? So based on that I can tell or I can vote for the manganese. But still, manganese cannot have the ferromagnetic property, that is the speciality. Manganese cannot have the ferromagnetic property, which is taken care by the iron, cobalt and nickel. That's what I told while discussing about the solid state. I was telling that ferromagnetism is related to domain, arrangement of the domain in the crystal structure. Right? It's not like paramagnetic where it is related to paired electron or unpaired electron. Here it is related to domains. How these domains are present in the crystal structure. Fine? So that's where, although manganese can have the high paramagnetic character, but still they cannot show the ferromagnetism. Some people later, some of the alloy of manganese, they have the ferromagnetic character, but as a manganese, no. Okay? So even iron, when I am talking about iron, if I heat the iron at 768 degrees Celsius, 768 degrees Celsius, iron will become, I am talking about iron only, so iron will become paramagnetic. It will lose its ferromagnetic property. It will become paramagnetic. That particular point, you people might have discussed in your physics, that is called as Curie point. What is Curie point? It is the temperature at which an element is going to lose its ferromagnetic property. So that's where iron at 768 degrees Celsius, it's going to lose its ferromagnetic character and it's going to behave as a paramagnetic substance at that particular temperature. Below that, no. It will become once again ferromagnetic. Fine. So what will happen at that high temperature? So they are going to disturb the domain structure of the crystal of iron. So due to that, what will happen? There will be random arrangement of domains will take place. So which can lead to disturbance in that ferromagnetic character. Fine. So therefore, how these individual domain in a solid structure, they are present, even they are going to decide whether it is a ferromagnetic or it should be a paramagnetic. But as a paramagnetic property, if I take, manganese should dominate because it is having highest unpaired electron. Yes, that's what Janani. You people might have studied this one in your physics.
So shouldn't chromium have most number of unpaired electrons? Even in subshells it has unpaired. S in
Okay,
subshell.
chromium. Chromium it will be 3d4,
3d5
4s2. 3d5 meant for manganese.
But 3d one of the electrons will shift to d subshell.
Okay, so when I am talking about chromium, it can have either 3d5, 4s1. That's what you mean to tell. So in that case, when I am talking about chromium, although if it is 3d5, 4s1, it is actually 3d4, 4s2, right? So 3d5, 4s1 if it is having to attain the stability. Now according to Mayank, since it is having unpaired electron in d subshell and unpaired electron in s subshell, it's going to have maximum unpaired electron. But when I am talking about unpaired electron, normally S subshell electron is not going to have much impact because they are having more affinity towards the nucleus compared to the D subshell electrons. So therefore, D subshell electrons will be considered, or it will be given more priority when it comes to magnetic property, paired and unpaired electron, if D subshell electrons are involved. Got my point? So that's where manganese I will give the preference because it is having 5 unpaired electron in its D subshell. Fine? Any doubt? This is very important because sometimes they will ask problem on this. Problem in the sense we have to have one equation and we have to find out the magnetic property. We have to find out the magnetic property. Now when I am talking about equation where mu is nothing but magnetic moment, mu is nothing but magnetic moment, magnetic moment is equal to square root of n into n plus 2 Bohr magneton unit. So this is nothing but Bohr magneton, which is a unit, and you have to mention the unit. So n is nothing but number of unpaired electron. N is nothing but number of unpaired electron. This is very important, very important for your exam. Okay, so what is nu? Nu is nothing but magnetic moment. N is number of unpaired electron, and Bm stands for the unit for your value. If you are simply writing the answer without unit, you are going to have the less marks. You are going to get the less marks. So Bm stands for Bohr magneton. Okay. Now, can you calculate for zinc what should be the magnetic moment? Fast. So for zinc it should be 0 because n value is equal to 0. So therefore nu is equal to 0 Bohr magneton for the zinc. Can you calculate it for manganese? Calculate it for manganese where 5 unpaired electrons.
5.8.
So where manganese, where n is equal to 5 unpaired electrons. So therefore nu is equal to square root of 5 into 5 plus 2 Bohr magneton, which is nothing but square root of 35, right? 5 plus 2, 7. Okay. So, yes, I think it should be 5.9 Bohr magneton. It should be approximately 5.9 Bohr magneton. No, Shiv Kumari, you cannot write 35 for Bohr magneton. No, its square root is there. You have to further solve it off. Okay? So, better you can further solve and you can find 5.9 Bohr magneton, approximate value. So, it will be approximately 5.9 Bohr magneton. So, can you calculate it for chromium? Can you calculate it for chromium? It is there, right? Yeah, all the elements they have might have solved. Fast. So it will be 3d5 4s1. Then I will take both the electrons, no doubt. I am talking about chromium. So mu is equal to n plus 2 Bohr magneton. Okay, fine. So what is n value? 6. Oh, it will be more than manganese, as Mayank has told. If I consider S subshell electron, Bohr magneton. Okay. Oh, it will be too large value. How much it will be?
Four into 1 point.
It will be too high value. Okay, approximately, okay. It will be 7 or
6.92.
Okay, 6.9. Okay. So it is greater than manganese. If I take as a element. Now if I go with common ionic forms. So this is as an element. If I go with common ionic form of these element. If I go with common ionic form of these element. So in that case, can we calculate it for manganese plus 2? How much for manganese plus 2? Apply the same equation. It will be same as that of the manganese. So it will be 5.9 Bohr magneton only. Right? So if I take Fe plus 3, if I take Fe plus 3, hmm?
5.9.
So it will be 5.9 Bohr magneton only, because Fe plus 3 is also having 3d5, right? So 4s0. Fe plus 2. If I take Fe plus 2,
6.9.
Fe plus 2. How much it will be? Fe plus 2. Ferrous. Ferric. Ferrous means 3d6.
4.9.
That means 3d6 means it is having 1, 2, 3, 4, 5, 6. That means 4 unpaired electrons. So that means nu is equal to 4 into 4 plus 2 Bohr magneton. How much it will be? 4.9. 4.9. 9 Bohr magneton. So that's where we can calculate the magnetic property for any of these elements. Magnetic property for any of these elements. So therefore, when we are talking about as an element, when you are talking about as an element, as Mayank told, we can consider chromium as an element if I take, right? But if I take it in its common ionic form, then manganese ion is going to dominate. But when I am talking about zinc or zinc plus 2, in both the cases it will be 0. So whether I am talking about zinc or zinc plus 2, it will have the 0 magnetic moment. Any doubt? Don't forget to write the unit. Many students, the answer will be perfect, but they will not write that BM, Bohr magneton unit. So therefore, they are going to lose the marks. Fine? Any doubts in this? Okay. Now, when I am talking about color, because most of the D block elements, transition elements, they will have the colored compounds. They will form the colored compounds. So whether I am talking about whatever we are wearing, right, all this crystals or whatever it is there, they are all colored because of the transition elements. They will be having the transition elements like ruby and all. Due to that, transition elements are present, they will have the different colors. So question can be, one more question can be, give reason for the color for the transition element and its compound. What is the reason? So one of the reason answer should be, it is due to DD transition, which is due to the DD transition. So what do you mean by DD? DD means Doordarshan. DD channel. So DD transition means, if for example, you people have studied about coordination compound, right? So if I consider that one, we have T2G, where 3 orbitals will be there, and we have the EG, where 2 orbitals are there, right? So triple G stands for grades. Grade means levels. Okay, now that's where we have the T2G and EG, where we can have dx square minus y square and dz square over here. Then we can have dxy, dyz and dxz here. So 3 orbitals here, 2 orbitals over there. That is because normally this d subshell, they are having 5 orbitals. They will not be in uniform level. They will be having variation. That's where crystal field theory talks about. So they will be split into 2 different levels. So 3 will be here, 2 will be here. Fine. Now, electrons might be present in this orbital. Now when you supply the energy, that can be in the form of light. When you supply the energy, so these electrons which are present here in lower level, it might be shifted to here. It might be shifted to here. So that means it has covered this much energy difference. It has covered this much energy difference. Now due to the DD transition, because those electrons which will come back once again, so during that time they are going to emit the radiations. They are going to give the color. That is one thing. Fine. Same way, we have another reason here is, say for example, I have a compound. You can take it as a transition element. Due to DD transition, what will happen? They will absorb some amount of energy which is suitable for these electrons to move to the higher level. So they will absorb that particular radiation. See for example, normally visible light can be red and blue region. Broadly we can classify it as red and blue region. If this element is absorbing red, then they will appear blue to us. because they are emitting the blue when they are absorbing the red radiation. Now if the same way I have another element H nu, red and blue, if they are absorbing blue, then they will appear red to us. So that's where we have the color to these particular transition elements, right? Say for example, if I take CuSO4, that is Cu2SO4. What do you mean by Cu2SO4? Cuprous sulfate. Cu2SO4 is nothing but cuprous sulfate, unstable molecule, no doubt, not very stable. So due to less hydration enthalpy for cuprous ion, so therefore it is bit less stable. But still, if I take cuprous sulfate, it is white in color. Okay. But if I take copper sulfate, that is cupric sulfate, if I take cupric sulfate, it is having beautiful color, that is blue color, sky blue. It will be having blue color. So that blue color is due to water molecules along with the cupric ion, Cu plus 2. Water molecules along with the cupric ion. So due to that, a transition element in different oxidation state can have the different colors. So cuprous form, it will be having white, but when it comes to cupric form, it will have the blue color. What is the reason for all these things? One word answer is, that is due to DD transition. That means movement of the electron at different energy level within the d orbitals. So that's why it is called as DD transition. All of you have understood? So therefore, due to the presence of DD transition, these transition elements will have the colors. They will form the colored compounds. Fine? Any doubts up to here? So this can be asked for 1 mark. Okay? With related to colored compounds. It can be asked for 1 mark. So what we have discussed today here is, that is related to redox potential, that is standard redox potential. So standard redox potential we have considered with M plus 2M and then M plus 3, M plus 2. So try to remember about scandium here, try to remember about zinc and manganese here, and try to remember why Fe plus 3 and Fe plus 2. They will be having positive ion. That is related to standard redox potential, which we have discussed. Then we have discussed about magnetic properties. Then we have discussed about magnetic properties. So where diamagnetic, paramagnetic and ferromagnetic. So when it comes to ferromagnetic, we have iron, nickel and cobalt. When it comes to paramagnetic, we have lots of element other than the zinc, which is diamagnetic in nature. Okay? Then you have to remember the equation for calculating the magnetic moment. You can expect 1 or 2 marks question on that problem. Okay? So any doubt? That's what we have discussed. And at the end we have discussed about the reasons for the colors for transition element and their compounds. What is the reason why they will form the colored compounds? So any doubt? For magnetic moment calculation, any element they can ask or any ion they can ask. To answer that, you should know the electronic configuration. Okay? Any doubts? No doubts? Okay. So I will stop here. Okay, once again. Oh, you want me to explain why that colored compounds, right? Now when I am talking about colored compounds, Purnima, so So when I am talking about colored compound, that is majorly due to DD transition. Okay. Now all of us we know why we are calling it as DD transition. All of us we know that in coordination compounds, you people have discussed, right? So crystal field theory. So where d orbital will be once again split into two different orbital or energy level, where we have T2G and there we have the EG. So once again it can be divided into two different energy levels, d subshell itself, right? So now there will be movement of electrons from here to here. Sorry, there will be movement of electrons from here to here because there is the energy level difference is there. So when this movement will happen, when they will absorb some amount of energy. When they will absorb some amount of energy. So that's where it is called as DD transition, because within the D subshell there will be movement of electron will take place. Why within the D subshell it will take place? Due to the presence or splitting of the D subshell into two energy levels. So due to that there will be movement of electron. Therefore it is called as DD transition. So now here what will happen? Some of the transition element among the red and blue region. If I take it as broad region instead of as VIBGUI, or I will make it as red and blue region. Red region is low energy region, blue region is high energy region, right? So if they are going to absorb the red radiation, if they are going to absorb the red part of the visible light, then they are going to emit the blue light. Then these elements will look like blue to us. They are blue in color. Same way, if I have the elements where they will absorb blue, then they are emitting the red, then they looks like red. In the combination it will be different colors. But to make it easy, I have given only two as the colors. Fine. So that's where we have the colors to the transition element, because this absorption will take place due to the DD transition. They will absorb a particular part of the visible radiation. So due to that, transition elements will have the colors. Fine. Now we have understood. Fine. Purnima, have you understood? So if you want to give the example, I took the example of cupric Cu plus 2, which will be having blue color, cupric sulfate or copper sulfate. Same if I take cuprous sulfate, it will be white in color. So what should be another factor? Another factor here it is oxidation state. What is the oxidation state of the element? Okay, fine. Okay. So thank you in that case. Tomorrow we are going to continue with the class. Take care. Bye.